Hello, everyone. My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems, coming to you from the Park Nanoscience Center on the campus of SUNY Polytechnic Institute in Albany, New York. Welcome to the 7th installment of Park Systems 2019 Material Science Research and AFM webinar series. Today's presentation is on the topic of smart proppants and oilfield productivity. Before we begin, let me give you a quick overview of today's session. The presentation is expected to take approximately 40 to 45 minutes, which should allow us some time for a question and answer period at the end. If you click the raise your hand button at that time, I can unmute your line to ask a question. If you would prefer, you may type in your questions at any time during the webinar, and I will try to pose these at the end. Any of these questions that we do not get to, we will try to address in a follow-up email. It is now my pleasure to introduce to you live all the way from Bangkok, Thailand this month, Dr. Rigoberto Advincula. Dr. Advincula is a professor of macromolecular science and engineering at Case Western Reserve University and the editor-in-chief of MRS Communications. He is a fellow of the American Chemical Society and is the author of more than 250 peer-reviewed publications. Please welcome Dr. Rigoberto Advincula.
Again, thank you so much, Richard, for that generous introduction. And indeed, I'm doing this webinar from another location around the world, Bangkok, Thailand, to be exact. And of course, I'd like to greet our audience. Good morning, good afternoon, and good evening, wherever you are, and thank you for tuning in. So today I'm going to talk about proppants and chemicals for hydraulic fracturing. The topic is quite specialized, but quite interesting because we will be looking at hydraulic fracturing and its contribution to the upstream of the petroleum industry. So first, let me talk about Case Western Reserve University and what we do and why our interest in oil and gas and petroleum-related research. So we are located in Cleveland, Ohio, and near the Lake Erie, a very cultural part of Northeast Ohio. We're at the home of the Cleveland Museum of Art and the Cleveland Orchestra. And I'm a professor at the Macromolecular Science Engineering Department. We are located at the 5th floor, and these are a picture of some of my crew members and number of work that represents the area of oil and gas materials research. A lot of the students who have finished the program, but also credits to some of my current students who work very hard to contribute to that field. Our area of research in general is interfacial chemistry, and we work a lot on nanostructuring and materials from colloids to coatings to surfaces and sensors. And this just represents some of our contributions to literature. On the other hand, we love to work with industry. A number of these companies in the past have funded our work, and also companies related to the oil and gas industries, including oilfield service companies and proppant companies, which I will highlight today, the work we do with propping agents for hydraulic fracturing. In a way, what we do in a university is to take the best of the basic platform of research that we develop and then translate it to the market. And the way we do this is, of course, with applied chemistry, applied materials, and working with companies, we are able to work on problem solving where we have a very good performance cost ratio. In other words, we do something that will improve efficiency or performance cost ratio. And of course, somebody will be willing to pay the cost. Now, the area of petroleum science and engineering, we started 2014 PetroCase, which stands for Polymers for Energy and Transformative Research in Oil and Gas. We work on materials that can be very useful for extreme conditions, proppants for unconventional oil and gas, coatings that can withstand high temperature, high pressure, as well as nano additives for improving fluid behavior and flow in various fluids used for the upstream industry. So the way we do this is we work with polymers. Polymers, as shown here, are large molecules with different microstructures, from linear to cross-link structures to random, hyperbranch, and of course, a lot of interest these days is in controlling their composition, microstructure, or their structure property relationships. In a way, you want to use these polymers to control fluid behavior. Fluid behavior, whether it's solution, emulsion, or suspension base, means that the polymers can control viscosity as an additive, can protect deformation as additive for controlling degradation and acid stimulation. It can be used to stabilize the formation during matrix acidization type of procedures. And in the upstream industry, we work with drilling fluids, completion fluids, workover fluids. So various fluids have an importance in improving productivity and the wellbore conditions or integrity. Now, polymers are not only solubilized, they can be micellized or contribute to the cross-link gel formation. They're able to phase separate between the oil and the water phase, or they can be involved in swelling and contraction based on controlled pressure and temperature. In other words, these are smart materials. They are able, based on the correct structure property relationship, have applicable stimuli responsiveness that allows them to be used smartly for controlling fluid behavior. So here I outline some of the more recent research work we do with the oil and gas industry, from working with viscoelastic surfactants and other wheel stimulation fluids, resin-coated proppants for hydraulic fracturing, which I'll emphasize today. We do 3D printing methods and projects, including nanocomposites, use of continuous flow polymerization methods to improve efficiency in polymerization of additives useful for the oil and gas industry, continuous and circulation testing under pressure and temperature. We do a lot of work on anti-corrosion coatings, and therefore we emphasize the use of superhydrophobic coatings for oil and water separators as well. And then lastly, we're interested in the application of nanomaterials like nanocellulose, graphene, and other nanostructuring methods for oil field chemical additives. Okay, here's a view of our laboratory. I just want you to see how it looks like. We are fully equipped for both synthesis and characterization. In particular, we're able to do a lot of surface analysis, including atomic force microscopy, which we do on coatings and also proppants. On the other hand, we're fully equipped for working with some projects related to core flooding, pressurized flow, rheology of fluids, fluid loss measurements, and investigation of phenomena that could be related to downhole conditions. Okay, so let me emphasize that in the oil and gas production and distribution, one deals with from upstream all the way to downstream. There are demands or problems that can result in low efficiencies or low production. That is why, for example, the emphasis on low cost but high productivity or high efficiency is always an attractive option. In fact, with proppants, which we will talk more about today, there is a drive to understand the cost of using a lot of proppants versus using smarter proppants, even though at a higher cost, but can result in higher production efficiencies. And such is the case for shale oil and gas. This has been the key towards oil and energy independence here in North America, in the United States in particular. So science and technology is trying to keep up always with regards to improving efficiency and problem solving. Now, as you can see here, we can divide the petroleum industry into the upstream, midstream, and downstream. And I apologize if this sounds simple for some of you who are experts there and who has been involved with the industry. I would like to use this as a segue also to address people who are very new to this field. So upstream regards to oil and exploration and production, which involves drilling and extraction. Midstream could be transportation and storage, all the way to the refining, and then of course downstream is refining all the way to the distribution. And all this means that there are various supply chains and production demands that starts all the way from the oil field. It could be offshore or onshore. Now, hydraulic fracturing is a game-changing technology that goes back, in fact, all the way 75 years ago. What it is that it allows you to extract unconventional oil and gas or difficult to extract resources such as shale oil and gas by employing high pressure pumping of various fluids, primarily aqueous fluids that has been viscosified with a polymer. Now, a key ingredient to hydraulic fracturing is not only the additives, but the use of propping agents or proppants. And this has largely been in the realm of sand or minerals, but in the past and even now, there's a lot of interest and uses of ceramics, bauxite, and other types of resources, including walnut shells and, of course, resin-coated sands, which emphasizes the work we are doing with polymer coatings for proppants. So just to emphasize that whether you're dealing with subsea engineering, drilling, transport, storage, or refinery problems, it's always a catch-up game in that the energy or efficiency of energy extraction increases or improves as the technology catches up. In fact, 10 years ago, people were talking about peak oil in that people thought that we have extracted all the oil and gas that we can ever do, or at least very difficult to do tertiary recovery until a lot of efficiencies have been solved or perfected even in the area of hydraulic fracturing, which brought the cost of doing such procedure to a very um, profitable price. Of course, the price of oil and gas fluctuates, and one can say that in leaner times, cross-cutting or conserving cash has always been a game. But remember that in this game, which goes up and down, technology is always a prime mover in all stages of the upstream all the way to the downstream of the petroleum industry. So here is just a very simple chart showing how the oil and gas that is extracted from the field is separated from oil and produce water, and then eventually goes to the gas processing power plant, transported by pipes, of course, and then compressed. And if it's transported as an LNG, of course, this is on the way to exporting, which is, of course, what the United States has become for the last 5 years. We are a net exporter of natural gas throughout the world. And then, of course, one has to deal with fouling problems, which is present in a lot of extraction industries. And that means that whatever we pump or we use in all of these pipes, whether it's the casings or the pipes that transport oil from the production field all the way to the refinery, there's always a lot of caution to add anti-scaling or anti-corrosion agents, or even the use of better alloys to prevent fouling. And then lastly, catastrophic failure is something that the oil and gas industry is very careful to avoid and or mitigate, at least by producing or using the best practices in the industry. So I hope this introduction at least have put a perspective on our interest in proppants and hydraulic fracturing. So before I focus more on proppants, a good introduction on hydraulic fracturing is needed. In hydraulic fracturing, a fluid based on water, oil, or emulsion uh, is pumped towards the formation, which we typically would say tight. So we have shale formation that has oil and gas resources. Now, together with directional drilling, or sometimes we call horizontal drilling, this has allowed the efficient placement of these um, tubulars or annulars properly such that the uh, formation, which have very high pay zones, can be reached by hydraulic fracturing. So typically, we're looking at about 10,000 to 20,000 feet. Pressures are about the same, about 10,000 psi. And therefore, anything you pump means that you have to pressurize or you have to viscosify the fluid such that you can force the opening or the fracturing of the shale and then eventually employ proppants. So most fracturing fluids will comprise of water, chemical additives, and the suspended proppants. The extended fractures will essentially uh, be opened or kept open by the disposition of proppants that are pumped together with the hydraulic fluid. A lot of these stimulation procedures are used in order to improve the production efficiency. In other words, without this stimulation or even completion procedure, these wells are unproductive. And this means that careful planning is needed to match the production cost or improvement of the fracturing procedure. Now, as you can see here, the hydraulic fracturing fluid is basically a carrier that pumps the proppant in as far as possible to the fracture. And this means that the fracture, which can be prepared by a perfed or isolated perforating method, uh, is able to crack them open or fracture them open such that the fluid that contains the proppant will be dispersed as far as possible in the formation or the fracture such that the proppant actually remains on that fracture and keeps it open. In a way, a proppant really is a tool that is employed during this procedure. Now, a good question is, if this is a tool that remains on the fracture, shouldn't we be emphasizing the efficiency of the tool or the proppant to enable higher productions? And this is probably a good question to answer or ask. Why is it that most hydraulic fracturing procedures have shorter lifetimes? In other words, within 1 to 2 or even 3 years, there's a high drop off in production with most hydraulic fracturing procedures. Now, simply put it, the efficiency and the planning that goes ahead with the hydraulic fracturing procedure is not really just the proppant itself, but the stages, the type of fluid used. So the proppant is just one of the factors that can affect the eventual productivity of the well. So a hydraulic fracturing fluid, of course, is mainly water in this case, although other emulsions or gases can be used. And as a hydraulic fracturing fluid, it contains many things, including gelling agents, surfactants, cross-linkers, breakers, inhibitors, biocides, and so on. So it's a formulated fluid, and together with the viscosifier, one is able to carry the propant together with this fluid on the formation. Okay, so a good fracturing fluid should be able to withstand various temperatures, pumping rates, or shear rates. As I said, most commercial fracturing fluids are aqueous based, and they are jellified or even foamed. And a typical jellifying or viscosifying agent is based on a polymer. Now, in the past, there was a lot of use or interest in the use of guar and santan gum. However, these days, people rely more on polymers like polyacrylamide to viscosify media or fracturing fluid that is used for fracturing. Again, the purpose of the fracturing fluid is to create a conductive path from the wellbore extending to the fracture, and secondly, to carry the propant material into the fracture to create a conductive path for the produced fluids to be extracted. Now, this table summarizes several types of base fluids that are used for fracturing: alcohol base, acid base, emulsion base, or even oil and gas base. A typical water-based formulation contains slick water, fluids containing cross-linkers, as well as viscosified water, and that could be synthetic or um, natural polymers such as guar, as I mentioned, that can improve the viscosity. Other types of fluids, from foam to oil-based, again have various functions and composition, but time will not allow me to focus on those other fluids because, as promised in this note, I'm going to emphasize more on propants. Lastly, I'm going to review to you what are the stages in fracturing. So first stage is injecting a prepad with a low viscosity fluid used to condition the formation, which can contain fluid loss, additives, surfactants, and prevent formation damage. The second stage will involve the generation of fracture in this shale formation, or in other words, a viscous fluid is injected without propants. So the purpose of this is just to create fractures as efficiently as possible. The third stage is then when you introduce the propant with the viscosified fluid. The goal, or the main goal of the propant, again, is to keep the fracture open or propped up, and that's why it's called propant, in short, short for propping agent. Okay, and that means the ability to control the density of that propant together with the fluid, and as well as able to disperse it together with the carrier fluid as far as possible is a very important objective. Okay. Now, after you've done that, you'd expect a certain flow back, and that means that you need to clean up the formation. Now, this is usually done with flash fluids, and eventually the fluid viscosity should diminish or slow down, and therefore these decreasing levels of viscosity is meant to clean up the well, but to leave the propant in place. And then finally, you need breakers, or these are chemical agents that are used to remove any gel or any polymer that is incorporated in the formation, as this may uh, result in formation damage or prevent efficient transport of the produced oil or gas through the fracture, and eventually the anchor zone, or the uh, uh, production area that connects it towards storage or head. So having outlined and giving all this introduction, let's talk about propants. Okay. Now, as I mentioned, propants are particles. Propants are propping agents. These are particles that are suspended with the fracturing fluid, or hydraulic fracturing fluid. The purpose is to create a high permeability at the formation pressure. Another purpose is, of course, to prevent uh, the pressure or the intrusion pressure or the formation pressure from closing the fractures, and therefore they have to have sufficient thermomechanical strength to handle the residual stresses or the formation pressure. And then secondly, of course, they need to have the right surface area or the right lubricity for the resource, whether it's oil and gas, to pass through. Now, in terms of materials, there are several choices, and I'm just going to name them. The most dominant is sand, followed by resin-coated sand, and then ceramics are used, followed by bauxite, and then high-strength bauxite. By the way, bauxite is a derivative from the aluminum refining industry, or it's an aluminum oxide composition. And as mentioned, all the way from sand to bauxite, there is a increasing resistance against closure stresses. In other words, even from this pyramid that is shown in this view graph, sand is basically a low strength material and more irregular in size and shape. Ceramics or resin coated sands are more conformal. They have medium strength, increased strength. And then finally, the ceramics or even the bauxites are more regular in their geometry as synthetic materials or synthetic particles. They can be highly valuable in terms of strength, resistance against closure stress, and of course, changes as far as the density or even compressibility. In fact, as mentioned, from sand all the way to bauxite, it's generally accompanied by increasing cost. In other words, sand is the cheapest material you can have, but it's actually the weakest. On the other hand, the ceramics uh, uh, that was actually produced by companies previously like Carbo or Saint-Gobain are premium, but they're more expensive, although they have the best resistance against closure stress. So really a good question that we can ask in the hydraulic fracturing business is, why is it that even though the sand is weak and more irregular in shape, it is used often. In fact, majority of the hydraulic fracturing uses sand. The answer is quite complicated, but I will attempt to use the word cost. Everybody wants to save costs. Everybody wants to lower the cost of um, completing the well, hoping that that lower cost will translate to a better economics on the project. But let me remind you a very important principle in any production industry. Lowering the cost or the capex is not always the best solution. The best solution is the right ratio between cost and performance. Uh, as you can see here, you have 3 or 4 choices of propants. And yet the industry or the oilfield service companies or even the operators always specify sand. In fact, a good number of projects or performance is rated towards pumping as much sand as possible or massively dumping, or not dumping, but I would say including in the fracture as much volume of sand as possible. Now, this has been reported to have given very good production efficiencies, but one should wonder if using the right tool or the right propant, one could have achieved even a higher production than what would have been expected. Now, such is the case for the oil and gas industry, especially the upstream. The upstream industry is a very conservative industry. Nobody wants to make a mistake. Nobody wants to be the person or the operate or the field service company to be blamed. And yet, everybody insists on doing what everybody else is doing. In other words, the industry does not look very much or even very kindly at propositions for cost versus performance or the balance between the two. So having said that, the objective of the rest of this talk is to show you that there are options for smart proppants. Okay, so roughly sand is the most used, but ceramics and resin coated sands are better in terms of performance. Okay, so sand is cheap. It is useful and has been proven to reduce high stress, but can improve permeability. On the other hand, it's also been proven that ceramic particles have a higher performance, especially against higher pressures or closure stresses. Other shell materials based on aluminum or magnesium has been used. Even walnut shell has been used. That is an irregular geometry versus spherical geometry. All have been proven to be useful at certain types of projects or even stages. So, for example, sand is commonly used when you have shallower wells or lower pressures. On the other hand, ceramics has been reliably used for more demanding higher pressures and deeper zones. Okay, sintered bauxite is actually a synthetic material. This has a lot of advantages in terms of size and resistance against compressibility. However, again, the economics does not dictate that this is used very commonly in massive amounts in wells. Other types of proppants that have been reported includes lightweight proppants such as those that have hollow shells or calcified or kaolin containing kaolin clay containing aggregates, and a number of this has been reported in literature and some talks. Other unconventional types of proppants includes fibers, filters, resin-coated proppants, as I'll emphasize soon. This has been very useful in that the main idea, as I said, is to prevent closure or prevent closure stresses in the fracture and keep it open as much as possible. Now, emphasizing resin-coated proppants, the game-changing part there is the polymer coating that is used to coat the proppants. In other words, we can take sand and we can coat it with phenolic resins, Novolac type of resins. And by the way, the phenol formaldehyde or phenolic resin is the most common type of thermoset resin coatings on proppants. So the idea is to improve the resistance or crush resistance of these proppants by armorizing or putting a thermoset shell of a polymer around these materials. However, proppants uh, prepared, let's say, in the manner of thermosets, can also be coated with other types of polymers. Remember, the word polymer is a bigger term than thermoset. Polymers can encompass thermoplastics, elastomers, other types of thermosets or combination of thermosets and or elastomers. So the key word here is really polymer coated proppants, and that could mean you are coating it with a thermoset, a hydrogel polymer, or even a thermoplastic polymer. And each can have possible advantages under real downhole conditions. Okay, so here I'm showing you several chemistry options for propants. The most common part is based on a phenol formaldehyde resin chemistry, as shown. Uh, this is the reaction basically of a phenol and a formaldehyde, very old chemistry, in fact, more than 150 years old. Bakelite comes into mind, the word bakelite. The word Novalac resin comes into mind. So these are basically cooked or mixed together with sand, and then finally coating it with a uniform thickness, uh, possibly, and giving the sand a higher crash resistance. Now, that is not the only type of resin coating available. The epoxy coating is also a well-known product. Epoxy comes from the reaction of epichlorohydrin and bisphenol A, but really there are many choices for epoxy or epoxy phenol formaldehyde combinations. Epoxy refers to the group that reacts together with the hardening agent or alcohol to produce a coating. And then other companies have, of course, reported polyurethane. Polyurethane is based on the chemistry of diisocyanate and polyol, the combination of which allows you to get, again, a thermoset resin material based on the number of cross-linkers, or in fact, polyurethane as a thermoplastic can be employed. Now, I'm not going to speculate on what other companies have employed so far, but other chemistries that are not shown in this view graph would involve polyamides, polyesters, okay? It could involve the use of uh, polybenzoxazine. In other words, you have a choice typically between thermosets and thermoplastics in using resin-coated sands. Sometimes it really is a question of economics in terms of, again, lowering the cost so that the coating can be done on a particular propant, especially with the right size, okay, or the right mesh size, which could be 20/40 or 40/60 or 60 to 100, okay. The mesh size really is a sheave size that is used to characterize the average size of the grain or particle. So having said that, let's look at some basics here. Um, One of the difficulties in maintaining the ability to transport a propant is specific gravity or density. So typically, the fluid itself, hydraulic fluid, is of a lower density. Sand and resin-coated sands have a lower density. However, particles like bauxite or ceramics have a high density. In other words, the specific gravity tends towards the value of 4, whereas your fluids typically have a value of 1 or 1 to 1.5. So the question is, what happens to a propant when you suspend it with a viscosifying fluid? The answer is, if it has a higher specific gravity, it has a tendency to settle, or as a suspension to settle or separate from the viscosified fluid. What needs to happen basically is for this propant to match the specific gravity of the fluid, in that is, you need to float, or you need to suspend, or you need to basically homogeneously suspend the uh, propant by having a lower specific gravity to match that of the hydraulic fracturing fluid. So there's a need, for example, to move this curve to lower specific gravity, but at the same time maintaining the high crash pressure resistance. Okay. So in other words, an ideal situation or ideal cost and performance ratio will be a ceramic that has a low specific gravity but very high crash resistance. Okay, let me repeat. An ideal propant will have a low specific gravity and a high crash resistance. I might add there, it should have a high compatibility with the fracture fluid. In other words, it should be suspended and should be kept suspended until it reaches the fracture so that it can be distributed more equitably on the fracture and therefore maintain its opening. Okay, now there are some factors here that I can quote based on an SPE report that affects the propant conductivity. And these 6 propant factors actually do not even account for its relationship with the fracturing fluid. Big error here, or big overlook in that propant as a particle is always suspended with the fracture fluid. So why is it that the propant only emphasizes size, strength, shape, concentration, ability to prevent embedment, and crash resistance? So this particular table, again, just emphasizes the propant itself, but does not mention its relationship with the frac fluid. So propant size ideally are particles anywhere from 12 to 20 mesh. Some have looked at 40 to 60 mesh. So the higher the mesh size, the smaller the particle. Propant strength, so this refers to the crush resistance or ability to withstand closure stresses and therefore maintain the opening. Propant grain shape, so a well-rounded propant, some people believe to be ideal, although as mentioned, walnut shell and other types of particle geometries have been used. Propant concentration, so the higher the propant, the better in principle. On the other hand, one can ask, is increasing the propant concentration really a key? So it's hoping really that the propant ends up in the fracture. But a good question here is, what happens if the propant simply dumps or settles somewhere in the formation and does not reach the fracture zone? Embedment, so propants basically end up embedding on the fracture because of the high closure stresses, and therefore they can reduce conductivity simply because they become part of the fracture. And then lastly, propants are broken into smaller pieces, and therefore these are called fines. The fines generated are much smaller particle sizes, and they can block the flow or fractures on productive zones. So all of these really are factors that may contribute eventually to low productivity in a well. Here I have summarized here some things that can be done. Propant can have anti-settling additives to keep it suspended. A propant can have uh, protection against flowback, or simply making the propant stay longer or even adhere on the formation. Okay, so some concepts here could be the use of thermoplastics, adhesive coatings on propants, or even magnetization. Okay, because flowback is a problem. Flowback means that the propant properly did not lodge on the fracture, and during flowback there could be enough pressure or flow to basically remove back the propants towards the fluid that is pumped out, therefore failing to lodge it on the fracture of the pay zones. Okay, so here is a list of some of the propant companies. Some of them may actually be defunct, but Proppant companies could mean the oilfield service companies themselves, the supplier of sand, the supplier of resin-coated sand or ceramic, and a number of these are based in the US as well as abroad. Okay, one particular Proppant that has been regarded to be uh, quite important for matching the specific gravity of the frac fluid is a self-suspending proppant from Fairmont Central. So in this case, a gel, a hydrogel, or actually a polyelectrolyte complex surrounds the proppants, and therefore it is able to float. It's able to disperse more homogeneously on the frac fluid, and therefore stays longer and ends up in the fracture zone. So one can see here in this simple demonstration that a typical sand will simply settle at the bottom. But if the same sand can be coated with a gel or basically a shell that swells with water, it floats. Basically, it viscosifies the fluid too. In other words, one possibility is the need for less friction and this reducers and viscosifier on the frac fluid because the viscosifying media actually surrounds the particle or sand itself. Now, this self-suspending propan actually has been patented. It's a commercial product by Fairmont Central, and the chemistry involved that of a hydrogel coating on the polymer. The hydrogel can be made up of different monomers that are capable of hydrogen bonding in various aqueous media or slick water conditions. And this hydrogel is compatible with other types of viscosifying media as well. And together with the additives, the patent actually looks at various compositions that is able to uh, have the hydrogel component stabilized together with the suspending propan. So anybody can look at this patent, but in analyzing this patent, they probably end up using polyelectrolytes here, some cationic polymers together with several viscosifying media. So this composition together with the hydrogel essentially swells the shell or the polymer shell around the particle. So this would have involved some coating process where the hydrogel is fixated on the particle, and therefore when resuspended in water, they're able to float, viscosify, or in other words, the swelling of the gel basically lowers the overall specific gravity of the particle itself. Now, going on to other types of propant technologies, from curable resin coatings to the incorporation of nanocellulose, many things have been reported, including fiber reinforcement for propants. Okay, some have reported even biodegradable propants to this effect, and some have reported the hollow shell ceramic propants. So, in the interest of time, I'm just going to go quickly and describe to you what we've been doing. So we have been working on coating particles with polymers using flow chemistry or batch processes. Basically, a particle can be coated with a polymer using surface-initiated polymerization. So this shell means that the polymer itself can be grown on the particle during polymerization. Now, we have demonstrated this using flow chemistry setup where we pack the column with particles, and then we introduce the monomer, and the initiator has been previously grafted on the particles as are shown here. For example, to coat this particle, the silica particles, with hydrogel based on pegmetacrylate, both homopolymer and black copolymer strategies. So here we coated the particle with polyethylene glycol methacrylate followed by polynipam or N-isopropyl acrylamide, which resulted in a hydrogel coating itself. We are actually able to test the permeability of fluids on these particles, measure the differential pressure or temperature under higher pressure and higher temperature conditions. So in other words, this could be a core flooding experiment that can be done in the lab. Okay, so let me close by pointing that one of the compositions we have done is based on the use of polybenzoxazine. Now, polybenzoxazine chemistry is a thermoset chemistry with a higher temperature rating. We've actually used it for coatings that can be used for oil and water separation or the formation of aerogels. As can be seen here, the benzoxazine ring is simply opened up by heating to produce a thermoset with a high degree of cross-linking. Now, skipping this curve, let me just focus on how we have proven this concept. So the polybenzoxazine can be coated directly on the particle. Once it has been coated and heated, you basically form a very hard shell. And we have tested the performance of this propant coated with polybenzoxazine using crash stress measurements and also unrestricted compressive strength measurements, and investigated their wetting properties using contact angle measurements, as well as measure the thickness using photoacoustic IR. And we have shown that these propants and resins have quite a high crash resistance. So the goal now is to coat these propants with a hydrogel, which we have also filed a provisional patent. The hydrogel, together with the high strength of the polybenzoxazine coating, for example, will produce a superior propant, which combines both low specific gravity and high compressive strength resistance. And then finally, we've done a number of measurements to look at the viscosity, shear rate dependence, propant pack behavior, and crude oil displacement, even with this type of particles, using a unidirectional pressure-driven flow measurements. Now, let me close by saying that atomic force microscopy actually is a very important tool for characterizing such resin-coated sands. We have some data, but I'd like to use this data that was recently published in 2017 by the Barron Group. What they did is they fixed carbon nanotubes using cross-linkers or modifying the surface of the propant, the ceramic propant, such that the carbon nanotube can be incorporated on the surface. This was investigated by both SEM and AFM, confirming the morphology changes as the carbon nanotubes are grafted on the surface. So with that, I've given you a lot of information, and I hope you find this useful. I would like to thank you and be happy to answer any questions that you have.
All right, thank you very much, Doctor. And I don't have any submitted questions right now, but if anybody has a question, please use the raise your hand icon or simply type your question into the questions tab on the GoToMeeting window. I'll give you just a second to type those in or raise your hand here. And it looks like we have one hand raised, so I will unmute the line for Claudio. Looks like you're self-muted. If you could, there you go. Are you there?
Can you hear me?
Yes. Please ask your question.
So my apologies. My calendar had this starting at another time on the West Coast time zone. I have two questions. One, is this presentation going to be available on video so I can share it with the rest of my team? And the second question is, did you speak about or have you investigated the opportunity to be able to look at fly ash when you think of silica?
I'll take the first one just on the availability. We do post all of the videos of these webinars both on our website at parksystems.com and our YouTube page. So
Great.
It just takes us a few days to get that process, but certainly by Monday you should be able to find that video. And then
okay, thank you.
To Dr. Advincula for the rest.
Yeah, no, I'll be happy to answer the second part of the question. Yes, the fly ash actually is a very important additive for several ways. One is it can be incorporated as part of the thermosetting chemistry to improve the cross-linking density, let's say with the Novolac resin or even the benzoxazine chemistry that we do. I think the question really is what quality of fly ash can be used, because it can be a source of, as you mentioned, silica and other types of particles. So if the size is right, it can be actually used to improve the shell quality. The other possible use of fly ash and other siliceous or particles of that nature could be in dispersing or providing better flow conditions of the proppant itself. So the proppant can be stored in a silo or in a cargo, and usually they have to be delivered, and caking is a problem or aggregation is a problem. So different types of silica particles or even some surfactants are used to prevent aggregation or caking so that the particle can flow better during transport or delivery.
It looks like, just as a quick follow-up, he also asked, is there an ideal size?
Well, the micron size, if the silica, let's say, could approach that of, let's say, 20 to 1 micron, is possible as a useful size. Actually, a competition material could be different types of colloidal silica or fume silica that is produced by companies like Cabot or Evonik. But certainly fly ash with the right dispersity, anywhere from tenths of microns, can be quite useful.
All right, in the interest of time, I'm going to start to wrap this up here. If you have further questions, continue to type them in or email them to me later. I will at richard@parksystems.com. I'll take this opportunity to ask my usual question, which is, can you give us a brief preview of next month's webinar topic, QCM and ultra-thin films tandem with AFM?
Yes, Richard. First of all, I'd be happy to interact with other members of the audience who may have further questions, and they can email you, Richard, or they can email me, and of course it will reach me either way. Regards to the next month's topic, this is an exciting topic where quartz crystal microbalance, an important technique in surface analysis, it can be used and combined, let's say, with techniques like atomic force microscopy or even electrochemistry to investigate in detail the properties of thin films, both dynamic and even some of their electrochemical qualities. So please tune in if this topic is of interest to you. We'd like to take that time to educate our audience.
Thank you, Doctor. Please join us for that session on Wednesday, August 21st, once again at noon Eastern Daylight Time. And thank you for joining us for this session of the Park Systems 2019 Material Science Research and AFM webinar series. If you have been enjoying the webinar series, we hope you will consider joining us for the 2019 Nanoscientific Symposium on SPM, held on November 19th and 20th here at the Park Nanoscience Center at SUNY Polytechnic Institute in Albany, New York. The symposium is a venue for researchers, scientists, and engineers to learn about the latest studies being formed using SPM, featuring speakers including Dr. Advincula and many other industry and academic experts. Visit live.parksystems.com for registration information. Thank you once again for joining today. You can find more information about Park Systems AFM at parksystems.com. And please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series, feel free to reach out to me directly, as I said earlier, at richard@parksystems.com. Thanks again, and we'll see you next month.